Hello friends, in this session we will see some old gate problems based on state space analysis as well as on compensators and PD controllers, PID controllers, PI controllers, etc. Let us begin. Yes dear, they are asking a differentiator has transfer function whose phase increases linearly with frequency or whose amplitude remains constant or whose amplitude increases linearly with frequency or whose amplitude decreases linearly with frequency. Let us try to check out. We all know that it is a differentiator. Differentiator means what? Definitely it is PD, right? And for that we have seen that the transfer function is nothing but KDS. Is that correct? KDS. Correct? Yes. So now if I just replace S by j omega, what do I get then? I get T of j omega to be equal to KD into j omega. Is that correct? Which is same as what? J KD omega. Is that correct? Yes. Now if I try to find what is magnitude, what is that? Magnitude equal to? Magnitude is nothing but what? Yes, magnitude will be nothing but KD omega. And what about phase here? Phase is nothing but, because we have this J, which means phase is nothing but plus 90 degrees. Now if you just check out this phase angle which is there, phase angle is constant. Is it there in your option? Is it there in your option? No. Now what about this M magnitude? Just think about, if this omega increases, what happens? Definitely magnitude also increases, right? Which means amplitude increases linearly with frequency. This is the answer. So option C is the answer. Correct? Yes. Let us see one more problem. Yes dear, it is gate 1998 question. If you see, the phase lead compensations used to increase rise time, decrease overshoot, decrease both rise time and overshoot, increase both rise time and overshoot, decrease rise time and increase overshoot. What is that? Let us see. We know that when we talk about lead compensator, lead means, right? Lead is same as what? PD. We know that. Now we know that PD is used for what? It is used for improving transient response, right? Or rather improving transient behavior. We have seen that. Correct? Yes. Improving transient behavior means what? Your rise time has to be less or more? Definitely rise time has to be less. What about your, what do you say, overshoot? MP? More or less. Definitely when we are talking about improving transient behavior, it means MP has to be less, which means both rise time as well as peak overshoot has to be less, has to be decreased. So answer is option B, decrease both rise time and overshoot. Correct? Let us see one more. Yes, it is gate 2003 question. If you check out, the lead compensator used for a closed loop controller has the following transfer function. This is the transfer function given. Correct? Now for such a lead compensator, they are asking you whether A is less than B, whether B is less than A, whether A is greater than K into B, and whether A is less than K into B. Correct? So if you remember, I had told you that whenever we talk about lead compensator, suppose I am standing at origin, what should I see first? When will I feel that I am leading in my life? Whenever I find 0 first. Correct? Correct? Yes. And then I should find pole, which means where is my 0 now? 0 is at A, minus A rather, and my pole is at minus B. If you see, what does this mean? This means that magnitude of B has to be greater than magnitude of A. Is that correct? Yes, magnitude of B has to be, or rather magnitude of B has to be greater than magnitude of A. Correct? Yes, which means B has to be less than A. See, I will tell you, don't get scared. For example, assume that this is at minus 2 and assume that this is at minus 3. Now this is your B, this 3 is your B, and this is your A. Is that correct? Yes. Is that correct? Yes. Now if you see what has happened now, what has happened now, this A is less than B or not? This A which is 2 and this B which is 3 is 2 less than 3? Yes. Which means is A less than B? Yes. Which means it is option A. Getting my point? Yes, that's it. Problem solved. Let us see one more question. Yes, it is GATE 2016 set 2 question. See, for the network shown in the figure below, the frequency at which the maximum phase lag occurs is, first of all, let us try to find the transfer function. Okay, now what will be the transfer function? If you see, in order to find the transfer function, we have to replace L by Ls and C by 1 by Cs, correct? Now if you check out here, C is equal to 1, so you get 1 upon 1 by S, so this can be replaced as 1 by S directly. Is that correct? Yes. Now let us think of V out, output voltage. By voltage division rule, let me apply voltage division rule over here. What do I get then? What will be this V out, the voltage across these two terminals? Definitely it will be total voltage V in multiplied by what? Multiplied by what? Multiplied by impedance across this V out, which is nothing but 1 by S plus 1, the whole divided by what? Whole divided by total resistance. Total impedance is what? 9 plus 1 by S plus 1. Is that correct? Which means you get V out to be equal to how much? V out to be equal to 1 by S plus 1 upon how much? 9 plus 1 is 10. 10 plus 1 by S into V in. Is that correct? If you just arrange this properly, you will get V out upon V in is equal to S plus 1 upon 10 times S plus 1 by 10. Correct? This is nothing but your G. Now, if you compare this with our GC expression, what was our GC expression? K into S plus 1 by tau upon S plus 1 by alpha tau. This was our compensator transfer function, right? Compensator transfer function. Okay, now if you just compare, what do you get then? What do you get then? You get that tau is equal to 1. So tau is equal to 1. Next is what? Alpha tau. Alpha tau is nothing but equal to 10. By comparison, right? S plus 1 by 10 we have here, and we have S plus 1 by alpha tau. So by comparison, we get alpha tau to be equal to 10. So alpha tau equal to 10. Therefore, what do we get? Since tau is equal to 1, we get alpha to be equal to how much? 10. Correct? Yes. Now, frequency at which maximum phase occurs. Frequency at which maximum phase occurs is nothing but omega, which is given by 1 by tau under root alpha. Correct? We have seen this particular formula. What does that mean? 1 by tau. Tau is what? 1 into under root of alpha is 1 by 10. What does this mean? If you solve this, if you have this in your calculator, 1 by under root 10, you will find it somewhere around 0.316 radians per second. So 0.316 radians per second is your answer. 0.316 radians per second. This is your answer. Correct? Now, let us see one more question. Yes, dear, it is GATE 2017 set 2 question. Now, the transfer function C of S of a compensator. This is transfer function of a compensator. The frequency range in which the phase lead introduced by the compensator reaches the maximum is. Let us try to find that. See, we will try to first identify which is, what do you say, lead and lag. Try to identify that. For that, let me consider the transfer function itself again. C of S equal to 1 plus S by 0.1. Okay. Now, if I try to draw the pole 0 plot, how does it look? See, you definitely find this 0.1. It is a 0. So you have a 0 at minus 0.1. Correct? Now, what happens here? Again, you have a 0 at 100. Correct? You have a 0 at 100. Okay, this is minus 100. Now, what next you have? It's a minus 100. Now, what next we have? Yes, 1 plus S tau. This is also 1. So definitely here you have somewhere you have 1. See, this is minus 1, let us say. And then what we have? You have S by 10, which means 10. So again, minus 10 is somewhere here. Correct? This is the pole. Now see, if I am standing here, what do I see first? I see 0 first, which means definitely this is lead and definitely this is lag, correct? Now, so whenever we say that the frequency range in which the phase lead, see they are asking lead introduced by the compensator reaches the maximum is definitely within this range only, within the range of the lead compensator. What is that range? That range is between -1 and 0.1, -1 and 0.1. So definitely for omega between 0.1 and 1, that is the answer, correct? Yes. So it is answer omega from 0.1 to 1. Option A. Option A is the answer. Now, let us see one more question. Yes, it is GATE 2008 question. The transfer function of two compensators are C1 is this one, this is compensator C1 and this is compensator C2. Now, which of the following statements is correct? What are they asking? See, C1 is the lead compensator and C2 is the lag compensator. C1 is a lag compensator and C2 is a lead compensator. Both C1 and C2 are lead compensators. Both C1 and C2 are lag compensator. Now we need to check what is correct. Let us see that. See, for that, let me have the C1 transfer function first. Is it 10 into s plus 1 upon s plus 10, correct? What is C2 transfer function? It is also same, s plus 10 upon 10 into s plus 1. Now let us see that. See, let me draw the pole zero plot. How does that look? Definitely at 1 I have got a 0. So definitely at 1 I have got 0, -1. And at -10 I have got a pole. So definitely there is a pole at -10. Similarly, here if you see in C2, what has happened? I have a 0 at 10 and I have got a pole at -1. This is the pole at -1. Now see, if I am standing here, what do I see first? I see a 0 first, which means this is leading, which means this is lead compensator. C1 is lead compensator, right? Now, next is what? Next is what? If I am standing here at origin, what happens? What do I see first? I see a pole first, which means definitely this is the lag compensator. So C2 is a lag compensator. What is the answer? C1 is lead and C2 is lag. So definitely this is option A. C1 is lead and C2 is lag compensator. Done. Very simple problem. Yes. Now let us see one more. Yes, it is GATE 1993 question. If you see, consider a second order system whose state space representation is of the form x dot equal to s plus bu. If x1 of t is equal to x2 of t, then the system is. Now see, let us try to see the options. First is controllable, then we have uncontrollable, then the third one is observable. You please tell me, we don't have any information about C matrix, then will we be able to talk about observability? No, because we know that it is like CA, right? Stuff like that. We have seen that, correct? Yes. Which means what? If, for example, you want observability matrix, let us say, which is 5 naught, it is nothing but CA squared, right? You don't have information about C. That is the reason you cannot talk about observability. So observable is gone. Next is what? Stability. Next is stability. Now, is there any information about matrix A given? No, that is the reason even we cannot talk about stability also. But yes, we can definitely speak about controllable and uncontrollable. Let us see how we can do that. If you see, they have given x1 of t is equal to x2 of t. Let me start with that. So x1 equal to x2, correct? Now let me differentiate on both sides with respect to t. What happens? I will get x1 dot which is equal to x2 dot, correct? Yes. Now I can represent it in the form of, let us say, x1 dot is equal to, let us say, a into x1 plus b into u. Yes, my choice, right? Similarly, I can also write x2 dot will be, which is equal to a times x1 plus b times u. How I can do that? See, because x1 and x2 are equal, x1 dot and x2 dot are also equal, which means these two equations are also equal. Getting my point? Yes. Now, if I try to show them in the form of a state space model, how does that look? it looks like x1 dot and x2 dot is equal to a into x. What is x? x1 and x2. Let me just not use this space and let me take it down. Yes, see, how do I show that? X1 dot and x2 dot in state space model. See, definitely this is the A matrix, and we will be having, let us say, x1 x2, right, plus, and what we have here, u. Now if we check out what is happening, it is x1 dot is equal to what? A into x1. So it is A into x1 plus b into u, plus b into u. Is that correct? Now is it on x2? No. Dependent on x2? No. So here I will get 0. Similarly, if you think of x2 dot, what is that x2 dot? What is x2 dot equal to? x2 dot equal to a times x1 plus bu. So this becomes again a times x1 plus bu, correct? But now we need to understand one thing. Can I write here also 0? Can I write here also 0? No. Why? Because both are equal. That is the reason here also I will get a and a. Why? Because the x1 and x2 are equal, right? Because x1 and x2 are equal, that is the reason I have to write here a. I cannot write 0 over here. Getting my point? Right? Yes. Now let us try to check our controllability. How do we check controllability? For that we use B and AB, right? We use 5C, which is nothing but equal to Bachchan, Amitabh Bachchan, right? Now what is your B here? What is your B? B is nothing but BB. What is your A into B? For that, let me try to find what is A into B. So A into B, for that it is A, and this is B. B is what? BB, correct? If I try to find them, what do I get? Row by column, first row by first column. What do I get then? I get A into A is nothing but AB plus AB is nothing but 2 times AB, correct? Similarly, row by column, second row by first column. What do you get? You get A into B is AB and A into B is AB. So AB plus AB, 2 times AB, correct? So what do we get here? You get 2AB upon 2AB, correct? Yes. What is their determinant equal to? Determinant is equal to what? B into 2 times AB minus B into 2 times AB, which is equal to what? 0. If it is equal to 0, we say that system is uncontrollable. Uncontrollable. This means it is option B. Answer is option B, uncontrollable. Now let us see one more problem. Yes, it is GATE 2002 question. Okay, the state transition matrix for the system x dot equal to ax with initial state x of 0 is, see, forget about initial state, forget about everything. Always remember, state transition matrix is only one, which is nothing but Laplace inverse of Si minus A inverse. That's it. So is this the answer? No. Is this the answer? No. Is this the answer? Wait, this is Si. Wait a minute, here it was inverse. Okay, sorry. So what is the answer? Is the answer? No. Answer is option C. It is Laplace inverse of Si minus A inverse. Why? You need to understand one thing. See. Because those people have given you initial state as x of 0. What is this particular expression? This is expression for x of t. This is not the expression for STM, not the expression for state transition matrix, but it is the expression for x of t. Please mind you, this is how those people play with you. Okay, now let us see one more question. Yes, it is GATE 2003 problem. What does it state? It states that the second order system starts with the initial condition of this matrix 2 2 3. Okay, without any external input. Okay, external input is not there, only initial, right? The state transition matrix for the system is given by this. This is the state transition matrix, e to the power 80. The state of the system at the end of 1 second is, that is what they are asking. Basically, what do you have here? You got x0, which is nothing but 2 3. What is u? Input is 0, they have given, right? Now, and they have given you e to the power 80, which is equal to e to the power minus 2t 0 0 e to the power minus t. Is that correct? Yes. Now, how do you find x of t then? X of t formula, we know it is equal to e to the power at into x of 0. If I substitute all of them here, what do we get? E to the power at, so it becomes e to the power minus 2t, 0, 0, e to the power minus t. Correct? Multiply by what? X of 0. What is x of 0? 2, 3. Now again, row by column. What happens here? E to the power minus 2t multiplied by 2. So you get 2 into e to the power minus 2t. Correct? 0 into 3 is 0. Then again, next row and first column. Next row is what? 0 into 2 is again 0 plus e to the power minus t into 3 is nothing but 3 times e to the power minus t. Correct? This is nothing but x of t. Now, you are supposed to find it after t seconds. So at t equal to 1, what is happening? Let us see. So I will just replace t by 1. So I get 2 into e to the power minus 2 and 3 into e to the power minus 1. And if you calculate in a calculator, you get the answer to be equal to 0.271 and 1.100, which is nothing but your option A. So option A is your answer, right? Now, we have seen all the interesting problems, whatever can be asked in the exam. We have tried to solve almost all types of problems such that it will become easy for you. Okay, now I will request you all to please practice it, practice everything, and all the best for your exam. This was the last lecture of our CS control systems. Okay, thank you very much.